In the last 2 years, my team has been working on the development of a distributed services platform for a large financial organization, a US-based financial organization. And there were quite a few interesting challenges and cross-functional requirements in this platform they are building because they want to move away from their legacy platform. And they have very strong requirements on auditability, fraud detection, anti-money laundering, analytics. So those requirements pretty much driven us to adopt event-driven architecture. And my goal here today is to share with you some of our learnings while we build this architecture, joining together microservices and event sourcing. I am Vinicius Gomes. I write about technology in my blog, and you can follow me on Twitter as well. I am from Brazil, and that's where my accent comes from. So the agenda for today, I would like to start discussing a little bit about the traditional microservices approach, and then introduce a few concepts around event sourcing. Moving on, we're going to talk about CQRS, Command Query Responsibility Segregation, which is another idea that fits pretty well with event sourcing. Next, I'm going to run a demo. I'll try to demonstrate in practice some of those ideas implemented in code. And we're going to finish with a summary and some conclusions. All right, to discuss the traditional microservices approach, I would like to run an example. And I'm going to use this example throughout the presentation to make it easier. So let's imagine an online restaurant with a very simple data model in which you have a menu with menu items. We have customers. The customers, they have delivery addresses, and they can open orders and place orders using the menu items. So pretty standard, no complexity. We could implement that in the traditional approach, like defining 3 separate services: menu, customers, orders. Each service would have its own database. Each service would expose an HTTP API for users to send requests, and they would exchange information using HTTP as well. So the data flow, just to exemplify, let's say that we have our user over there with her smartphone, and she wants to open a new order in our restaurant. So she uses the device to send a post request to the restaurant. Then orders will pick that up. Orders will have to fetch customer information from customers, and then fulfill the original request, returning a response. So pretty simple workflow. Now, when the user wants to add an item to an existing order, it's pretty much the same. A post request to orders. Then orders needs to fetch information from menu and comes back with the response. In summary, we can see that approach as using HTTP methods to interact with resources. And those resources would more or less represent the entities in our domain. So some things about this approach is, the first one is that it's quite simple to implement. And it's technology agnostic in the sense that every technology today has some sort of support to work with HTTP. So it should be simple to implement a system like that with pretty much any tech stack. So next, I would like to just point out a few challenges on the traditional approach, which my team actually faced. And first one is coupling. So when services, they need to exchange information in the traditional approach, they need to explicitly know about each other. So if service A depends on service B, service A needs to know how to reach out to service B, how to parse responses, so on and so forth. Which means that resilience is also a problem. Let's imagine that our user here wants to interact with a restaurant. And let's say that the menu service is down. So now the user wants to add an item to an existing order, sends a post request to orders, orders tries to fetch information from menu, but menu is unavailable. So we're going to return an error back to the user. That means that order service is not resilient, and the entire system is not resilient because one service goes down and we cannot fulfill the user request anymore. Another problem is that when we have too many HTTP requests internally going on, that starts to impact the performance of the response time. And speaking about the HTTP methods used as a way to express the user intent to interact with resources, they're not very accurate to express the domain language of the user intent. So think about the user saying, I want to add an item to my order, and translating that to a post request to /order/ID/items. There's an impedance mismatch between the two languages. And most importantly, in my opinion, is the problem that this traditional approach can only handle the current mutable state. There's no way for us to have any insights on what happened in the past. There's no way for us to track the user behavior over time. And that brings us to event sourcing. Let's see how ideas behind event sourcing can help us to minimize those problems. All right, to speak about event sourcing, I believe a good way is to divide it in four main abstractions, which are the commands, which represent changes you want to perform in the system, events, which represent successful changes that happened in the past, the event store, which store all the events that happened so far in a chronological order, and the current state of the application, which is pretty much a projection of the event history. So let's talk about each one of them in a little more details. And the first abstraction we want to talk about is the most important one, which are the domain events. So the domain events, the orientation is to model something that happened in the past, and they have two very important properties. They are immutable, meaning that once you create an event, you can never update the data inside the event. And they're permanent. You never get rid of an event. Once it's created, you never delete it. So they're usually represented with some sort of declarative language, like XML or JSON. And they contain metadata and a payload. The payload has the interesting data from the problem space. So once we have the events, we store them in this specialized data storage, which is the event store. The event store is an append-only database, meaning that you can only perform inserts in it. And it's sequential. We try to keep our events in a chronological order in the event store so that it gets easy for us to retrieve them and apply them later. And it's long-lived, meaning that we intend to store our events, in theory, forever in the event store. We don't want to get rid of events, never. So once we have an event store full of events, for us to do anything meaningful with the application, we need to be able to rebuild the current state. And that's done using the aggregates. Aggregates are a concept from domain-driven design, which play a very important role in event sourcing. So the process of building the state of an aggregate can be described as a reduce function, in which we have a reducer function responsible for performing transformations depending on the event type. We have an initial data structure, which is usually an empty object, and the list of events. And the result of this operation is the current state. So for the ones who are familiar with JavaScript and Redux, it's pretty much like a Redux store. Let's see one example. Let's imagine our online restaurant, and there's an event store full of events from the online restaurant. And on the left, you can see there's an empty data structure representing our aggregate. So when we want to rebuild the state of the application, we're going to go in a chronological order, event by event, and perform the transformation. Let's imagine that the events in the bottom, they are older than the events on the top. And now we start to pick up the events. The first one is order open event. It has a payload with an ID only. And the transformation it performs in the aggregate is creating the representation of an order with an empty list of items and status as open. So we move on to the next event, which is item added. In the payload, we have a reference to the existing order and an ID for the payload for the item and a quantity. And when we perform this transformation, then we have an item added to the list. Moving on, we have another item added event. Pretty much the same thing, now a different ID, a different quantity. We apply that, we have another item added to the order, as you can see in the items list. Next, we have item removed event. So this contains a payload, in the payload, the item reference and the order reference, and it's going to remove one of the items. So as you can see, we are back with only one item in the list. And the final event is order placed. So in the payload, it only contains a reference to the order. And the only transformation it's going to perform is to change the status. So now the status is placed. And that's the order aggregate in the current state of the application. So imagine how powerful this concept is. We have a detailed description of the user behavior, and you know what happened and how it happened. And that can be useful in a range of different applications, like analytics, fraud detection, and even to debug the application, it's helpful. So we know how to rebuild the state of the application based on the event store, but how do we create new events? That's done using the commands. So the commands are just an abstraction to represent the user intent to perform a change in the system. So let's say that the user says, I want to add an item to an existing order. That's translated to an object, which is the command. The command has a type, which is the most important property in the command, and the type name usually translates to the user intent in the domain language. So if you read add item to order, you can easily translate that to the add item to order command. Like events, the commands, they have also metadata and a payload. The payload contains enough data for us to be able to perform this change. And it's also usually described in a declarative language. It doesn't contain any logic, shouldn't contain. So the process of handling a command in a typical event sourcing application can be described as with a function signature like this. Given the current state of the application and an incoming command, we run business logic and produce events. If something goes wrong, we throw an exception or just return an empty list of events. But usually, the execution of commands should result in events being created. OK, now we know about the domain events. We know about the event store. We know that you should use commands to create new events. But in applications exposing an HTTP API, how do clients send commands to the system, right? So there's no standard answer for that question so far. People have been talking a lot about this, but there's no definitive standard so far. So before we answer that, I would just like to review a little bit of the ideas behind the REST architecture, especially in regard to resources. So we usually have resource collections, which represent a collection of entities, more or less, in an application. So for instance, /orders would represent all the existing orders in the system. We also have individual resources representing individual entities, like /order/ID would represent a single order. We also have nested resources, which are resources inside resources. In this example, we have /order/ID, /item/ID. That's a particular item inside a single order. And we interact with those resource collections and nested resources using the HTTP methods. And most importantly, we have also the hypermedia formats, which describe how we're going to represent the resource data and the links between resources. Cool. So with that in mind, turns out that commands can be represented as resources as well, as opposed to HTTP methods. And for us to do that, there are pretty much two general approaches. There are more than two approaches, but they are pretty much variations of those two. And the first one would be to have a commands endpoint nested with a given resource. So clients would, by default, send a post request to an URL like that. And in the request body, they would specify the command type. In this case, we would send an add item to order command and would send that payload to orders ID/commands URI. That's quite simple to implement in the backend. You just need to define an additional endpoint. But for client applications, it gets tricky because now the clients, they need to know about all the possible command types they can send to every resource in your system. So we ended up implementing that in a different way. We decided to define a unique URI for each of the commands in the system. So we would have still the /commands endpoint, but we would also add a short version of the command name in the URI directly. That way, the client applications can send post requests to this URI and send just a request body without the command type in it. So that gets very flexible for client applications because they now can discover dynamically what commands are available for every resource, right? So in this example, I'm not sure if you can see it there, but there's a /order/ID/commands URL, and when clients get that URL, they receive a list of links with the commands they can send to this resource. So as you can see there is add delivery address, cancel, place the order. So things like that. So wrapping up, event sourcing is pretty much based on those four abstractions. We create commands, send commands to the system. The commands will generate events, which will be stored in the event store. And the event store will be used by the aggregates to reproduce to project the current state of the application. Now, how do we perform queries in an event sourcing application? Here's some bad news. The event store is not very good to perform complex queries. We usually store the events as blobs, as documents. So it gets tricky to perform joins. And so that it gets really hard for us to write any type of very complex query in an effective way in the event store. Moreover, in most applications, we have a lot more reads than we have writes. And that's especially true for banking applications. For instance, the bank customer, she would check the credit card balance or credit card transactions way more times than she would perform a payment. She would perform a few payments per month at most. So because of that, we had to use another idea, which is usually comes together with event sourcing, which is CQRS. CQRS stands for Command Query Responsibility Segregation. And this pattern tells us that we can divide our application into separate data models. The command model, in which we write data, and the query model in which we read data. So a typical CQRS application would look like this. So let's imagine that we have a service here. On the top, we have the command model. The command model usually contains an aggregate. We try to model our services around a single aggregate, and we call it a bounded context. And it's connected to an event store. On the bottom, we have the query model, which is connected to a query database. And the query database is a denormalized database optimized for search. So the way the data flows in an application like this is like that. So the user sends a command. The command is handled in the command model, and we generate an event, which is stored in the event store. And we end up publishing an event to an event bus, which is a separate component. on the query model, we're going to have a listener to that particular event or to whatever event we are interested in. And that listener will update the query database, which is connected to the query model. And the query model will serve the data for the customer to fetch it. So it goes like a circle like that. So we always write data to the command model, but we never read data from the command model. And similarly, we always query data for the query model, but we never write data. The user never writes data in the query model. That's done only through the listeners. Can I save the questions for the end, please? Thank you. All right, how do applications communicate when they are secure REST applications? The short answer is that they don't communicate directly anymore. They do that through the event bus. So two interesting things will happen here. Let's say that the service B depends on data on the service A. Whenever the service A publishes an event to the bus, both the service A query model will pick up this event in the listeners and it will update the query model, and the service B query model will also do the same thing. So most probably, the query model in service B will have a different structure, different representation of the same data as the service A, because they might be doing different stuff. They are different domains. So as long as they can deserialize the event, they can like build their arbitrary data structures that matters for the domain. In summary, in the command model, we have all the command definitions, we have all the event definitions. We have usually a single aggregate. We have an aggregate repository, which is a component that reads data from the event store and rebuilds the aggregate. And we have a write-only API, accepting post requests. On the query model, we have the event listeners, all the query entities, which are denormalized data structures optimized for search. We have repositories serving the entities and a read-only API. Nice. So we saw that we have the commands, we have the events, we have the event store, we have secure REST applications. Let's see how we could implement that using our online restaurant example. So in the online restaurant right now, we could refactor it in a way that every service would be a secure REST application. So pretty similar to what we already discussed. On the top, we have the command model with a command API, one aggregate, one event store, connected to the event bus. On the bottom, we have event listeners connected to the query database and entities connected to the query API. We still have the three services from the original example, menu, orders, and customers. They don't communicate with each other directly anymore. Now they do it through the event bus. And they are identical internally. They are all secure REST applications. Interesting things that will happen here in the demo. When we add a new item to the menu application, let's say that we are the restaurant staff and we want to enter data in the menu service. Menu will publish a menu item added event. And the order service will listen to that event and update its query side. Something similar will happen between the customer service and the order service. When users sign up, we're going to have customer signed up event. And when users register addresses, we're going to have address added event. And for both events, we're going to have listeners on the order side. So the state of the entire system will be like asynchronously, globally consistent. So I coded this demo using pretty much the same tech stack my team is using right now. We use Java, and we use Spring Boot to build our services. We use the Axon framework, which is pretty useful. It provides us all the basic abstractions for event sourcing and secure REST. On the query side, I use Spring Data REST. Since all the logic happens on the command side, we can just serve our repositories as APIs already on the query side. as long as they are read-only. And I use Rabbit MQ for the event bus. So if you want to see all the details of this demo, you can go to my GitHub. It's everything there. All right, let me switch to the demo here. So I have 3 services here running in my terminal. In the first tab, we have the menu. In the second tab, we have customers. Third tab, we have orders. And let's see them running here. By the way, I'm using the H2 database embedded, so I'm also using the H2 console. So here's the query API for menu. As you can see, in this items collection resource, we don't have any items added so far. And here's the H2 console for it. All right. So I do not have a separate database instance for the command side and to the query side here. Everything is in the same instance. But our event store here is a domain event entry table. So here in customers, we have an empty list of customers. We also have the database here. Let me just make sure we are connected to the database as well. And orders. All right. So what I want to do before I show the code, I want to create a few items in the menu. I want to sign up a few customers and open an order. I think that will be enough for us to see the services interacting. OK, so we are exposing commands as resources here. So as you can see, one of the links in this items resource is /commands. So if we send, if we navigate here to the commands, we can see that there's only one thing we can do with this items resource, which is add. So that will add a new item. So let's send a post request to this URL. I already have some requests set up here. So I'm going to add 4 items. I'm going to send a post request to menu items commands add with a payload like this, with a description and a price. And let's see what's going to happen. So as you can see, we get some URLs in the screen. That's because every request will return a URL in the body. We do that because since the command execution do not provide any data back, it just provides success or failure. We should return to the user an URL so that user can fetch the data in the query side. I'm returning in the request in the response body here directly, but you could use the HTTP location header most of the times. So we do that because we are guaranteeing to the user that the event was successfully created and it's navigating in the bus, but it might not be available in the query side yet. So we just provide the client application an URL so that the client application can go there and fetch the data. So let's see what happened here. Now in the query side, we have a few menus added. Pepperoni, margarita, 4 cheese, spinach and feta. And if we take a look at the events, you can see that there's probably 4 menu item added events here. Cool. So this data, as you saw here in the API, it's available in the query side as well. And here we have an item table in the query side, which has a friendly query-friendly representation of an item. And as we discussed before, order service will be listening to this event. So here in the logs, we can probably see 4 menu item added events on the orders service being handled. So if we navigate here to the last tab, which is the orders database, you can see that there is a menu item table. And it contains the items we just created. but in a more simplified way, because order service only would store the data it needs to add items to orders. So it doesn't have the complete version of the item. Cool, so we have items, and orders is now consistent with the new items we added. So let's sign up a few customers. So first, to do that, we need to see what command to send. And then we navigate here to the commands link, and that will tell us that there is a sign up command. Again, I already have some requests set up here. So we're going to send a post request to customer/command/signup with the payload, with the email address only. And we're going to also add a few delivery addresses and another customer, just to make things more interesting. So we run that. Again, we have references to the entities being created in the query side, so that the client application can go there and fetch. And now we have our new customers already available. And we probably have the events. Let me go to the payload type column here. So as you can see, there are a couple of customer signed up events and a few address added events. So now we can finally open a new order. But first, let's just make sure that orders is aware of the new customers added. So if you go here in the customers table, which belongs to the query side in orders, we can probably see, yes, a very simplified version of the customers just added. We just need the ID. We don't need any other information from customers. If the client application needs a detailed information of the customers, they would have to fetch that from the customer's domain. And that's pretty much it. Let's see if we can open an order. So again, for us to open an order, we need to discover what command we should send, and go here to /orders, navigate to the commands, and you see there is open. By the way, for every entity created, I'm not sure if you noticed, but we can check the commands available. For instance, this customer, we can change email, we can verify. So let's send a post request to create a new order. Open order. So we're going to send a post request to /orders/commands/open with a payload, which just contains a reference to the customer. And let's see how it goes. All right, we got a new URL back. It's probably going to be available already. And here's our order. So total cost, total price is now 0 because we didn't have any items in it. It's not placed yet. And if you see the order items, it's an empty list. If you see the commands available here, you can see that we can add delivery address, cancel the order, place the order. So I believe that at this point you already got the idea. So let's move on and take a look at the code, high level. And for that, I would like to keep this slide open for us to map back every component you're going to see in the code. So starting from the command API, let's take a look at menu, which is the most simple service. So this is a Spring Boot application. And here we have three very important packages, which is command, events, and query. So the events, they contain all the events that belong to this menu domain, which is menu item added events, menu item modified events, so on and so forth. On the command side, we have the API. So let's take a look at the command API when we are adding a new item. So there's a controller here, a Spring Boot controller mapping this particular URL, menu/item/commands, and there's a post mapping to add. And the most important part of this controller is that we are using the Axon framework to send a new command to the aggregate. So what's going to happen here is that we are going to create a structure like that. It's just a value object. It's pretty simple. And that's the command. It has an ID and a description and a price. And this ID should match the aggregate ID. Since we are now creating a new item, and our aggregate is menu item itself, so let's take a look at it. Like I said, since we are creating a new item when we have the add menu item command, we can map the constructor of the aggregate to a command handler notation. That will make that every time we send that command to the aggregate, that method will be executed. And as you saw earlier, in the aggregate here, in the aggregate side, we're going to handle the commands, and then we're going to perform some business logic. In this case, it's really simple. We're just ensuring that the description is present. And then we are going to save the event to the event store and publish the event to the event bus. And that's done by this apply method here. What it does is ensures that we're going to have a two-phase commit that will save the event to the store and will publish the event to the bus successfully. If any of those two operations fail, we're going to roll back the entire transaction and return an error to the user. And that's pretty much it for the command side. We saw the command API, we saw the aggregate, and the aggregate calls apply to save the event we created. And let's take a look at the event. Here's menu item added event. So it's just a value object, enough for us to deserialize a JSON object to it. Doesn't have too much. And now if we move to the query side in the bottom, the first thing we have are the event listeners. So of course, the menu service will have a listener for menu item added event. And if we navigate here to the query package, we're going to see that listener. Menu item added event listener. And that's pretty dummy. It only uses a JPA repository to save a new item, which is the query representation of an item. Again, just an entity, pretty much a value object. And the query API, since we are using Spring Data REST, we don't need to write any controllers. We just need to use a repository like this with repository REST resource and making sure that it's read-only. So we're not going to expose, save, and delete. Cool. That's pretty much it for a single application. So let's see how the order service gets updated when we add a new item. So it's pretty much the same thing. And when you navigate to the order service here and go to the query side, there's probably a listener for menu item added event. And what it does is pretty much the same. It uses a JPA repository again to save a menu item representation on the order service. And this one has only ID and price. So that's how orders gets to know about new items added. Cool. That's it for the demo. I have, like I said, all the code in GitHub if you want to take a look. I'll be in the conference until Wednesday, so we can chat more if you want. I think we can go to the summary now. Cool. So bridging microservices and event sourcing together in the same architecture. The benefits that my team is mostly happy about. We can start by history-based queries. So event sourcing provides you a way to know everything that happened in the past so that you have flexibility to answer history time-based business queries. Stuff like how was how many cancel orders we had as of last week compared to this week, or how many times a customer left the system without adding any item to the order. So interesting stuff like that, which would be a little bit tricky to do in a traditional system. Also, we have audit log by design. So in certain domains, like the banking domain, having an audit log is a quite strong requirement. And if you have an event store and you are working with event sourcing, you don't need to build anything else other than just having the event store. Immutability is another advantage. Since the event store is immutable and the command handlers, they are like pure functions, they are idempotent, you don't have the problem of, everything is thread safe, you can scale the application safely. Also, commands are a better fit to represent the user intent. It provides you better semantics than HTTP methods to translate the user intent in code. Decoupling is another advantage. Since the services, they don't depend directly with each other anymore, the only thing that they depend is the event payload. If they are able to deserialize an event payload from the bus, that's OK. It doesn't matter who is sending that event to the bus. So that gets pretty flexible when we want to refactor and move around who is sending an event. And resiliency is another advantage. Since we get consistent globally, asynchronously, all the services, when they are interested in some data, they just have a listener, and whenever that event happens, the listener will update the query side, so the data is always available immediately, pretty much. So in our example, when this menu service goes down, in our event sourcing version of the restaurant, the order service would be able to still provide the functionality to the user. And of course, we face a few challenges while building this architecture and watching this architecture in production. First one is complexity, right? There are more moving parts. There's more code to write. There's more tests to write, more things to maintain and coordinate. Also, as the amount of events increases and you have a very big event store, that starts to impact the performance when you are rebuilding the current state of the application, so that you have to maintain snapshots and then replay only the most recent events on top of it, and that's more complexity. And since the event store is immutable, there's no room for database migrations. When you change the payload structure, you have to write functions that will map old versions of the event to the newer versions of the event. And again, that's more code to write, more tests to write. Race conditions are another problem as well. So in theory, there's no guarantee in which order the events will arrive to the listener side, the consumer side. So the listeners, they should be aware of that and provide compensating actions when events are out of order. Event contracts are very important as well. So in order for us to make sure that we're not going to break consumers when we change the event payload, we need to have, at least in our CI pipeline, some sort of a contract test that will ensure that consumers can still deserialize newer versions of the events. And eventual consistency is another problem in the client side for client applications. So the only guarantee that the client applications can have from the command side is that the command was successful. But the data might not be available yet. So there are a few options that you can handle that situation, but pretty much writing more code on the client side as well. So my final message is that if you believe that your team would benefit from having an architecture like that, if your requirements, they fit with this model, that's something that you need to sit down with your peers and evaluate the challenges and the benefits, because it's, of course, more costly to build an architecture like that. But in our case, at least in our domain, we can safely say that the benefits, they pay off the challenges. And that's it for today. I'm going to be in the conference until Wednesday, so if you want to talk more about it, if you want to know more details, just reach out. I'll be happy to have a chat. If you have questions, that's the moment.